Hello friends, welcome to today's session. So today we are going to start a lecture series covering all the previous year GATE questions. So I hope this will be beneficial to you. So let us start. We will be starting through from the electromagnetic subject and followed by the other subjects. So let's start today's session. Yes, today we are going to solve a question which is displayed already on your screen. This question basically belongs to the subject, as you already know, EMTL, electromagnetics. Yeah, this question came in the year 2021 for 2 marks. So what is the first thing which comes in our mind? The first thing after looking at any question or after getting any question paper, first we should read the question very carefully. So let us start with reading the question carefully. Okay, the question says a standard air-filled rectangular waveguide with a dimension A is equals to 8 centimeter and B is equals to 4 centimeter operates at 3.4 gigahertz. For the dominant mode of wave propagation, the phase velocity of the signal is Vp. The value of Vp over c, where c denotes the velocity of light, is. So now what is given in the question is we are trying to propagate our wave in a rectangular waveguide with some dimensions it is mentioned. So we will talk on this. Followed by that, it says the frequency of operation is 3.4 gigahertz, and then it is also saying that our wave is propagating in dominant mode of operation of your waveguide, and we need to find a ratio of phase velocity over the velocity of light. So let us start. First, before we start the question, let me quickly draw the waveguide, a rectangular waveguide first. So here we can see, just a minute. Here we can see this is our rectangular waveguide. Here this is a three-dimensional waveguide. So generally this rectangular waveguide, basically the axis we are giving here in general nomenclature, this always be an x-axis, this is considered as y-axis, and this where the direction of propagation is considered as your z-axis. So always on x-axis the width is taken, which is always greater than the height. So here A is equal to 8 centimeter is your width and B is equal to 4 centimeter is your height. Now the question also clearly mentions that the frequency of operation of this waveguide is 3.4 gigahertz. Here in the question it is already mentioned that the waveguide is operating in a dominant mode. So the question arises, what is dominant mode? So now before talking about the dominant mode, let us first see the general solution of electric and magnetic field. So the general solution is given by E vector is equals to Ex Ax cap plus Ey Ay cap plus Ez Az cap, and magnetic field is vector is given by Hx Ax cap plus Hy Ay cap plus Hz Az cap. So now we have two different types of wave propagations. Basically there are two different types of waves. One is transverse electric wave, that is we called as a TE wave, and other is the transverse magnetic waves called as TM. So one is transverse electric and other one is transverse magnetic wave. So now, as per the definition of this TE and TM waves, we can say that the transverse components of electric and magnetic field exists, and the component in the direction of propagation, that is, if the direction of propagation is z direction, then in TE wave, that is transverse electric wave field, the component in z direction of electric field will not exist, and similarly for TM wave, Hz will not exist if the wave is traveling in z direction. So now we will just mention it, see which components exist and which components do not exist or equals to 0. So we have two waves with us. Let us say TE wave and second is TM wave. So I will just separate out here. As we have already discussed, the component in the direction of propagation will not exist. Then the components in the direction of propagation, that is our z axis, are Ez and Hz. So for in transverse electric wave, Ez will be equal to 0, and in transverse magnetic field, Hz will be equal to 0. The other components such as, let us say, Ex, Ey, Hx, Hy, Hz will not be equal to 0, and in case of TM wave, the components which will not be equal to 0 are Ex, Ey, Ez, Hx, Hy. Fine. So now we know that which components are here 0 and which component is non-zero. So let us go to the, first of all we will go to the next page, and let us go to the next concepts. Now you might have heard about the Maxwell equations. So after solving this electric field and magnetic field using the Maxwell equation for your TE wave, let us consider your Hz component first. I will let you know why I am not considering other components, but first try to understand this part. Hz will be equal to Hz naught cos of m pi by a in x direction, cos of n pi by b in y direction, e power minus gamma z. Okay, and similarly for your TM wave, we will be considering the Ez component, which is Ez naught sine of m pi by a x sine of n pi by d y e power minus gamma z. So these are the two things. So now let us first discuss why I am not considering Ex, Ey, Hx, Hy components, and I am only considering Hz and Ez. So basically the thing is, whenever a wave is traveling in some direction, so we need to have some or the other non-zero component in that specific direction. And if Hz, for let us consider the T wave condition, if I am saying z is equals to 0, then already for TE wave Ez is 0. Now Hz is also 0. So you cannot say that wave is propagating. It is getting attenuated, which we don't want. We want a propagating wave so that we will be able to solve our problems. Already we have given that wave is propagating. So we need to check all the conditions of propagation, not of for attenuation. That's why we are considering only Hz and Ez components. We are not at all worried about the other components in x direction and y direction, because that will not say that wave is propagating or not. That will only show you the characteristics of those waves. So that is the reason why I am just considering Hz and Ez component. Okay, that is Hz for TE wave and Ez for TM waves. Otherwise, for TE wave, Ez is equals to 0 as we already discussed, and for TM waves Hz is equals to 0. So let us go further. Now let us see point which is given already in our question, dominant mode. So the biggest question arrive here is, what is dominant mode? By definition, dominant mode is the lowest possible propagating mode, that is lowest possible propagating mode. It is lowest possible propagating mode which has a lowest frequency, of operation. And let us consider, if you want to talk about in the wavelength aspect, it will have a highest wavelength, because frequency and wavelength are inversely proportional to each other. Fine. Now we have here TM wave and TE wave. So now, to understand how this dominant mode is coming, we need to understand two things. First is TE MN and second is TM MN. So here this MN and this MN are some integers which can take a value m comma n, can take value from 0 comma 1 comma 2 comma 3 dot and so on. But one thing you have to take care in your mind, that if m and n both are 0 at the same time, the wave cannot propagate. So Mn can take value from 0 till so on, whatever you want, but please take care that you are not considering T00 mode or TM00 mode, as your wave will not be able to propagate, and again you will be getting a non-propagating attenuated wave, and that is not a correct thing. So that's why Tm and N, I will just write it down here in a small place, M and N cannot be 0 together. Okay, so now let us see, let us go to first next slide, and now let us see what are the combinations which are possible for your TE MN mode. The combinations are TE 10, TE 01, TE 11, and so on. And for your TM wave, TM MN, the combinations which are possible are TM 10, comma TM 00, 01, then your TM 11, and so on. So now this T10 is the lowest combination, followed by, it will increase as you are increasing the nomenclature. For in case of TM, again TM10 is the lowest nomenclature. So now let us see which of these modes are valid and which are not valid modes. So for this we will just have a quick glance. So here let us consider first your TE10 mode. Here for in TE10, value of m is 1 and value of n is 0. So let us go back to last slide where we have written Ez and Hz equation. Here we have written Hz and Ez equation. So now as we are talking about our T wave, so presently we just need to put our m and n values here in this equation. If I am putting the value of m as 1 and value of n as 0, now we can see this first cos component will take some arbitrary value based on your dimension A, but it will not be 0 right now. And but here, as we are putting n as 0, so we have to deduce this as our cos 0 degrees or cos 0 radians, which is 1. So we can say TE10 mode is a valid mode. TE10 mode here is a valid mode. So now let us say, now we can say as TE10 mode is the lowest possible mode. So in TE mode 10 is a possibility. So we can say for T wave, T part, T10 is a lowest possible mode. But we are not looking for lowest possible mode only. We are looking for a dominant mode. So in dominant mode, the mode which is lowest in both T and Tm is considered. So now let us write down. Let us consider here again as Tm10 mode. Here m is equals to 1 and n is equals to 0. Now in the last slide you need to put 10 for Tm wave. But as you can see, for both m part and n part, here you have an sinusoidal function. So sin 0 is always 0. So if one of the m and n is 0, Ez will not exist, Ez will be 0 and it is not a valid mode. As we have already discussed, we want Hz for T wave and Ez for Tm wave as non-zero quantity. So again here coming, then we can say Tm mode, Tm10 mode, Tm01 mode, where here you have m equal to 0. So both of these modes are not a valid mode, right? So now when we consider this Tm11 mode, we can see from this Ez equation that sign, when you will put 1 in place of m and 1 in place of n, it will take, Ez will take some non-zero value based on the values of A and P. So we can say Tm11 mode is a valid mode. So now we have two lowest possible mode. One lowest possible mode for T wave, that is TE10 as we can see, and for Tm wave it is Tm11, the lowest possible mode. So out of these two we can clearly conclude that TE10 is your dominant mode. Okay. So now let's move ahead. So now we have understood what is dominant mode. So now out of this we need to write the cutoff frequency. First of all, we need to find out our cutoff frequency. So now how to find out our what is a cutoff frequency? So now the cutoff frequency is nothing but the minimum frequency that is needed so that a waveguide which acts like a high pass filter functions. So I can draw a very small passband diagram here, as you might have already seen these kind of diagrams for the, this is your frequency. So now this is your stop band for high pass filter and this is your pass band for high pass filter. So for lower frequencies the waveguide always attenuates, and for higher frequency the waveguide allows propagation. So you can just, if you want, you can go and understand these concepts in the waveguides question from 2019. So there we have clearly discussed properly what is cutoff frequency in detail. So right now I'm just considering directly. So formula, so we will go to next slide. So the formula for the cutoff frequency for the dominant mode TE10. Why we are considering dominant mode is dominant mode always works on lowest frequencies. So that's why we are considering, generally we try to propagate all the waves in dominant mode. So now the formula for the cutoff frequency in TE10 mode is FC10 is equals to C over lambda. So this is a general formula, you know, but in TE10 mode it will be, we can say, the value of wavelength is equals to twice of the width, the greater part of the waveguide, that is A for us in this case. So it will be modified to C over twice A, which will, you can calculate by putting C, value of C is always is equals to 3 into 10 power 8 meters per second, and value of A is already given as 8 centimeter. So just while putting, just try to convert either meters in centimeters or value of A in centimeters in meters, so that you will get a proper answer. So I will not be doing the mathematics here, you can do it by yourself. So it is directly 1.875 gigahertz. You can do the calculations and check whether this is coming properly or not. It will come. So now, so we have cutoff frequency now, but we are not here to find the cutoff frequency. We just need to find our phase velocity. So now the phase velocity, the formula for phase velocity in TE10 mode is given as Vp is equals to C over square root of minus in bracket of 10 over F square. So now here we will see what are the parameters we already know and the unknowns for us. So here you can see Vp is unknown, we don't know the value of Vp, but we know the value of your C, FC10 we just calculated here, and F is already given as in your question as 3.4 gigahertz. But we don't need to, we are not trying to find out value of phase velocity. We are trying to find out the value of a ratio which is phase velocity to the velocity of light. So now the formula now will be changed to Vp over C is equals to 1 over 1 minus FC10 over F square, and it is in the under root. So now when you will solve this, put a value of 1.875. So I will write it here. Root of 1 minus in bracket 1.875. It is given as a gigahertz, but I will not write I will not be writing 10 to the power 9 value, because this 10 to the power 9, this giga part, and for frequency of operation giga part here will get cancelled, and the final answer here will have 1. So final answer here is 1.1987 something. But in the question, as you can see, we have already been asked, we have to round off to the 2 decimal places. So while rounding off to the 2 decimal places, we will get it as 1.0. So this is our ratio of phase velocity of light, that is Vp over C, as 1.20. So this is our final answer. So in GATE, generally you will find out different types of questions. Few questions will be a multiple choice questions where you will get A, B, C, D, 4 options, and few questions will be like the in the blanks type question where you have to calculate some value. There will be always a numerical type answers. You have to calculate some value like what we calculated here, 1.20, and you need to put it. So what is there any advantage of these kind of questions? Yes, there is one very good advantage of this kind of question, that these fill in the blank type of questions will not have any negative marking. The multiple choice questions where you have 4 options, maybe you get some help from the options while solving to some concluding something, but you have a negative marking, 1/3 of the total marks, that is for if the question is of 1 mark, you will have a negative of 1 by 3, and if the question is of 2 marks, then you will be having the negative of 2 by 3. But here in this numerical fill in the blanks type questions, you don't have any negative marking.